Hello and welcome to today's video. In this video we are going to briefly discuss the connection between scalar products and matrices in R to the n. So this is called scalar products and matrices. And we'll start with an example to see how this connection might work. We'll use R to the 2 as our example vector space, and we'll use a matrix that looks like this. It's a diagonal matrix with 4 and 5 on the diagonal. And we'll define a function using that matrix. Let's call it S. It's a function that takes 2 arguments, 2 vectors, and produces a real number. And it works by assigning to the vectors x and y the value x transpose times A times x. So you'll notice this looks almost like the canonical scalar product. If you replace A by the identity matrix, then this is exactly the canonical scalar product. So the question is basically, what properties does a matrix A need to have for this to be a scalar product? So the question is here, is S a scalar product? Or more generally, under which conditions on the matrix A will such a thing be a scalar product on some R to the n? And that's the question we're investigating here. So let's have a look at the properties of a scalar product, right? First property, remember, we needed to have a look at the scalar product of a vector with itself. So this is x transposed ax, or in this special case, well, it's x1, x2, times the matrix A, which is 4, 0, 0, 5, times x1, x2. And if you look at this, well, what do we get here? x1, x2 times, so this matrix times this vector, that is 4x1, 5x2. And if we do this multiplication here, we get 4x1 squared plus 5x2 squared. And as you can see through these squares here, and 4 and 5 are non-negative as well, this is surely non-negative. And also, S of xx is 0 if and only if x1 squared equals x2 squared equals 0. And that means x is the vector 0, 0. So that's exactly the first property. That holds. And of course you can see this depended actually on the numbers in here, right? So any diagonal matrix will do as long as the numbers are positive, or at least non-negative. Yeah, positive. We need positive. What about non-diagonal matrices? Not quite sure. So we might have a look at that later for general matrices once again. The other two properties are not that complicated. If we look at symmetry, then we can see S of x and y is defined as x transposed AY. Now in this very special case, the matrix A that we have is symmetric. And that means we can do the following thing. We can take this here. That expression is a real number. So we can just transpose it without changing anything. And this transposition, by the rules of matrix multiplication and transposition, you know this is the same as y transposed, A transposed, x transposed, transposed. So this is yt, at, x. And in this case here, it's the same thing as y transpose AX because A is symmetric. And you can see this works for general symmetric matrices. So this is S of Yx. And that means a function of that form will always be symmetric if the matrix is symmetric. And finally, what about bilinearity? So we need to have a look at S of lambda x plus mu y comma z. That is defined as lambda x plus mu y transposed AZ. And we can just apply the rules of matrix multiplication and of transposition here to get this is the same thing as lambda x transposed AZ plus mu y transposed AZ. So obviously this is the same as lambda s of x and z plus mu s of y and z. And this worked independently of the matrix, right? So we didn't need any special properties of the matrix here. So that means S is indeed a scalar product. And we've also obtained some insight into the properties the matrix needs to have. It needs to be symmetric for that second property here. And in addition, well, this first property is more complicated. This expression here needs to be non-negative for all x vectors. And it needs to have the property that x transposed AX is 0 if and only if x is a 0 vector. And that's not automatic. That's a very special property. So we'll have to we'll have to demand that property. But if we do that, then any mapping defined this way here will actually yield a scalar product in R to the n. And that's the connection that we were after. So let's summarize that in a theorem. It also contains a definition. Actually, we start with a definition. And this definition gives a name to that property that we need for the first scalar product property. So 1. If we have a symmetric matrix, it's also quadratic, of course, a symmetric matrix A in R to the n by n is called, now this property is known as positive definiteness. So the matrix is called positive definite if it has exactly the property that we want, and that is x transposed AX is positive, strictly positive, for all x in R to the n, excluding the 0 vector. And of course, you note if x is the 0 vector, then this property is automatically 0. We don't have to take care of that. As long as it's strictly positive for all other vectors, we're good. So in this case, for a positive definite matrix, this first property will automatically hold. And this is the actual theorem here. So part 2. For a quadratic symmetric and positive definite matrix A in R to the n by n, a scalar product on R to the n is defined through setting the scalar product of x and y, and we usually use the matrix A as a subscript here to denote which scalar product we mean. And this is defined through x transposed A y. In particular, the canonical scalar product is also one of that kind. The canonical scalar product is equal to the case A equals IN. So if you take the identity matrix, then we get the canonical scalar product, right? Because this is exactly x transposed IN times y, and of course multiplying anything with the unit matrix, with the identity matrix, IN doesn't change anything, so that's exactly the same as x transposed y. So the canonical scalar product is a special case of this more general matrix scalar product. But remember, the matrix has to be quadratic, it has to be symmetric, and it has to be positive definite to fulfill these properties, and then it induces a scalar product. So this concludes this little introduction into the connection between matrices and scalar products. And we'll continue our investigation of scalar products and specifically of orthogonality. That's a notion they define in the upcoming videos, and I'll see you then.